Hello guys, hope you have been having a great day. As promised earlier in my previous video that I'll be doing a video for Mason's gain formula with a pair of non-touching loops. So this question is an example for that. So you can watch the other video too, just the previous one, for a better understanding. But still, you can watch this and understand it without any prior knowledge, I'll say. So, as we know that this is a signal flow graph, R of S, which is the input, and C of S is the output, and we have different stages in here. So, our duty is to find out the transfer function C of S by R of S. So, C of S by R of S is equal to how much? And we are doing that by using Mason's gain formula. And to find out all that, exactly 5 steps are involved in this. And let us do them step by step. Step 1 is finding out how many forward paths are in this signal flow graph. So if you can see the arrow marks, how many of the arrow marks are going forward from C of S to R of S? How many paths are there which will take you from R of S to C of S? If you observe clearly, you can go in the complete straight path, which is path 1, or you can choose another path which goes till here, and this, like this. So, number of forward paths, our step 1 is forward paths. And we have 2 forward paths. The first forward path is the straight line from 1 to 6. 1, 2, 3, 4, 5 and 6. And the gains are G1, G2, G3, G4 and G5. So this is the first forward path. And in order to, why I'm finding out the first forward path is to find out the gain of the first forward path. So the gain of the first forward path is P1, and P1 is equal to G1, G2, G3, G4 and G5. This is the gain of the first forward path. Now let us find out the second forward path. As you can see in the signal flow graph, the second forward path is 1, 2, 3, and then it jumps to 5 and goes to 6. So the second forward path is like this. 1, 2, 3, 5 and 6. Now the individual gains are like this: G1, G2, G6 and G5. So, if you want to find out the gain of the second forward path, it is P2 is equal to G1, G2, G5 and G6. So the gains of the first forward path and the second forward path are here, which is P1 and P2. So, I'll use the other part of the board for now, but I think I'll be erasing this later. So just grab a picture of what it is here right now. So now our second work is to, the step 2 is to find out how many individual loops are there in the signal flow graph. So if you look at the signal flow graph, do you find out any individual loops? You can find out a loop between 2 and 3, between 3 and 4, and also between 4 and 5, and also between 3 and 5. So we have 4 individual loops. That is how you find out individual loops. So also you need to find out the gains of each individual loop. I think I'll erase this, it's going to be better. So note down the values of P1 and P2. We are going to need them later. So there we go. We have the values of P1 and P2. Now I am finding out the number of individual loops. So the first individual loop is from 2 and 3. And the second individual loop is between 3 and 4. G3, and the reverse path gain is H2. And the third individual loop is 4, 5 and back again. So 4, 5, this is H3 and this is G4, 4 and 5. Now the fourth individual loop is 3 to 5, but do you see this coming in the reverse direction? No. So the loop is not just like this. The loop is going from 3 to 5 and then coming from 5 to 4 and then again from 4 to 3. So the loop is going to be a little bit different, like this. It goes from 3 to 5 and comes back from 5 to 4 and goes back to 3. This is going to be our loop. So now mark the arrows and write down the gains which have been given in the question. There we go. So now we have all the 4 individual loops of this system, of this signal flow graph. Now find out the gains of each individual loop. So I'm going to denote the gains of each individual loop with P11, P21, P31 and so on. So my P11 is equal to G2H1. Simple, just multiply it. This goes G2 and the reverse path is H1, and P21 is equal to G3H2. And now you can say things. And P31 is equal to G4H3, right? And P41 is equal to G6H3H2. So now we have the gains of 4 individual loops of the signal flow graph. Once we have the 4 individual loop gains, now we are done with step 2. So just to create some space, I'll erase these things. I hope you're clear with this. And I'm writing these down here. These are for forward path and P11, P21 is G3H2, P31 is G4H3, P41 is G6H3H2. Right. And these are for the individual loops. Step 3 is to find out if there are any non-touching loops. So in the previous example which I solved, I didn't take the signal graph which had non-touching loops. So what we mean by non-touching loops, I actually explained in the previous video too, but what exactly I mean is, are there any 2 loops which do not intersect or which do not touch each other? Yes, we have this loop and this loop which do not touch each other. So if you take this loop and this loop, they are touching each other. If you take this one and this one, they are touching each other. If you take this and this, yes, they are touching each other. But the only pair of loops which is not touching each other is this and this. So we have one pair of non-touching loops. So the step 3 is all about pair of non-touching loops. And you are going to find out the product of the gains of the non-touching loops. So step 3. The 2 loops are G2H1 and G4H3. So these are the two loops, and the gain of this loop is G2H1 and the gain of this loop is G4H3. So the third step is all about the gain products of the non-touching loops, and this is denoted by P12, P13, P14 and so on like that. So now I have this product as G2, G4, H1, H3. So this is my product of the non-touching individual loops. So even this, I'm writing it down here. Non-touching loops. Now we are really closing in on the sum. We are in the final or the pre-final step, step 4, which is the calculation of delta and delta K. So before we actually start look into the fourth step, let us see what the Mason's gain formula is. So the Mason's gain formula is that C of S by R of S is equal to 1 by delta into sigma K, Pk and delta K. So as you can see, 1 by delta is the same for everything. Sigma Pk delta K. So P1 delta 1 plus P2 delta 2 plus P3 delta 3 and so on. But in our case, P1 and P2 we have already found out, which means this sigma has two things, which is P1 delta 1 and P2 delta 2. So that means P1 and P2 we have already found out, and delta 1 and delta 2 we are yet to find. And the value of delta is what we are going to find out in step 4. And delta 1 and delta 2 are also going to be found out in step 4. And once we are done with that, we can just put them all together in the Mason's gain formula. So I'm just putting this aside for now. Now, step 4 is calculating the value of delta. So value of delta is nothing but 1 minus the sum of the individual loop gains. The sum of individual loop gains. The sum of the individual loop gains plus the sum of the product of the non-touching loop gains. So the individual loop gains in this scenario are minus G3H2 plus G2H1 plus G4H3 plus G6H3H2. There we go. 1 minus the sum of the individual loop gains plus the product, the sum of the products of the non-touching loop gains. So in this case we have only one pair of non-touching loops. So we are going to write only one term there. And what is that? G2, G4, H1, H3. I hope you're clear with this step because this is pretty important. Delta is nothing but 1 minus the sum of the gains of the individual loops plus the sum of the products of the gains of the non-touching loops. So that is our delta value, and that's pretty simple. So I'm just going to simplify this and write that down as minus G3H2 minus G2H1 minus G4H3 minus G6H3H2 plus G2, G4, H1 and H3. So that is my delta value, and now we need to find out delta 1 and delta 2 because we have P1 and P2. To find out delta 1, consider the first forward path. The first forward path is the straight line like this. That is the first forward path. Now if you look at the first forward path, just look at it. Just look at the first forward path. Is there any loop in that signal flow graph which is not touching the first forward path? Is there any loop in that graph which is not touching the first forward path? The answer is no, because if you take this loop or this loop or this loop or this loop, they are all touching the first forward path. So delta 1 is equal to 1. Okay? So delta 1 is equal to 1. Now look at the second forward path. What is the second forward path? G1, G2, G6 and G5. G1, G2, G6 and G5. That is our second forward path. Look at it. Look at it. So if you see it, is there any individual loop which is not touching for the second forward path? Is there any loop? Just look at it. So so let's solve it by looking at each individual loop. If you look at this loop, it's touching the second forward path at this node. It's touching it at this node. If you look at this one, this loop, it's touching it at this node. But if you look at this node, it is also touching it at this node. So in this signal flow graph, there is no individual loop that is not touching the second forward path or the first forward path. So the delta 2, which we are going to write down using the second forward path, is also equal to 1. So delta 2 is equal to 1. So now we have the values of delta, delta 1 and delta 2, and we also have the values of P1 and P2. So all that is left is to use the Mason's gain formula to find out the transfer function. So I'm writing down the, delta 1 is equal to delta 2 is equal to 1. And that's the value of delta. So now, coming to the Mason's gain formula, which says T, that is a transfer function, is equal to 1 by delta sigma pk delta k. And in our case, that is equal to 1 by delta into P1 delta 1 plus P2 delta 2. Yes? You got it? Okay. So now, delta 1 and delta 2 both are equal to 1. So substitute the value of delta, P1 and P2. So that is equal to P1 is G1, G2, G3, G4, G5 plus P2 is G1, G2, G5, G6 by the value of delta, which is 1 minus G3H2 minus G2H1 minus G4H3 minus G6H3H2 plus G2, G4, H1 and H3. So this is my C of S by R of S, and this is what I actually wanted to find out from the given signal flow graph. So I want you to look at all this again. So the first thing we did was found out how many forward paths are there in that signal flow graph. Look at the arrows. Look at the arrows given in the paper and find the forward paths first. Once you have the number of forward paths, write down the gains of each forward path. Step 1, done. Step 2, find out the gains of each individual loop in that signal flow graph. So how many loops are there in that graph? Write them all down and write down the gains of each individual loop. Done. That is step 2. Step 3. Find out how many pairs of non-touching loops are there in that graph. Once you're done with that, write down the product of the gains of each pair. So in our case there is one pair, but if there were two pairs of non-touching loops, you need to write the products of the gains of two pairs of non-touching loops. So that is step 3. Step 4. Calculate delta, delta 1, delta 2, so on. How many forward paths you have, those many delta 1, delta 2, delta 3, so on. But delta is just 1, and delta is nothing but 1 minus the sum of the gains of individual loops plus the sum of the product of the gains of non-touching loops. So that is delta, all done. So that is step 4. Now step 5 is finally putting the Mason's gain formula into practice, and that is equal to 1 by delta sigma of pk delta k. And after that, all you need to do is really substitute the formula for substitute the values of P1, P2, delta 1 and delta 2. So, and how do you find out delta 1 and delta 2? All you need to do is look at the forward paths, and depending upon the number of times the forward paths intersect with the individual loops, or the number of times the loop, if any loop in that signal flow graph does not touch the forward path, then your delta 1 is 1 or your delta 2 is 1, as in our case, and as it is mostly is. So this is how you use the Mason's gain formula to find out the transfer function from a signal flow graph. And I hope you found this informative and useful, and if you have an exam tomorrow, all the very, very best. Thank you and have a lovely day.